In this example, we're going to do a more complicated problem involving the integral test. So we're asked to determine whether the series n equals 1 to infinity of 1 over n squared plus 6n plus 13 is convergent or divergent. So to be able to apply the integral test, we need to identify a function that we're going to integrate, and then make sure that that function is eventually continuous, positive, and decreasing. So if we let the f of x be 1 over x squared plus 6x plus 13, well, one of the things that we notice is that the denominator here is never 0. And we'll definitely see that here when we actually do the integral. But you can check, say, using the quadratic formula, that this has no real roots. So the function x squared plus 6x plus 13 never crosses the x-axis. So it's certainly, and since we certainly have positive values here, it's never going to be negative. So again, it's continuous, it's always positive, and it's certainly always decreasing because this denominator is going to get larger and larger, and the numerator is a constant. So this clearly satisfies the three hypotheses that we need in order to be able to apply the integral test. So we'll take the integral from 1 to infinity of the function, replace the improper limit with a variable, and let that variable go to infinity. Now, this particular integrand, we need to use a technique that we've learned before in order to be able to figure out an antiderivative. In particular, we need to complete the square in the denominator. Remember, for completing the square, we take half of the coefficient on x and square it. So in order to be able to factor it as a perfect square. So x squared plus 6x plus 9 is a perfect square. Well, to keep everything equal, if I have a plus 9 here, I must have a plus 4 left over to get that to be 13. We can factor now that x squared plus 6x plus 9 is x plus 3 quantity squared. So now we're looking at integrating 1 over x plus 3 quantity squared plus 4. We recognize this as an inverse tangent integral. It has the form 1 over u squared plus a squared. U is x plus 3, and the a would be 2 in this case. So an antiderivative is 1/2 inverse tangent of x plus 3 over 2, evaluated from 1 to b. We plug in our endpoints. As b goes to infinity, certainly b plus 3 over 2 goes to infinity. So our inverse tangent of something going to infinity goes to pi over 2. Times 1/2 gives us pi over 4. When we plug in 1, we get inverse tangent of 2. So when we evaluate this limit, we'll get pi over 4 minus 1/2 inverse tangent of 2. That number doesn't matter. All we really care about it is that it is a number. It's a real number. That limit exists. So the improper integral converges. And since the improper integral converges, the original series also converges by the integral test.